Now let us come back to the statement of the Riesz representation theorem. So recall that it said that if you have a locally compact Hausdorff space and a positive linear functional on that on the space of continuous compactly supported functions on X, then there exists a sigma algebra B lambda which contains all the Borel sets. So the Borel sigma algebra lies inside B lambda, and a unique Radon measure mu lambda defined on B lambda such that the linear functional lambda f is given by the integration against this measure mu lambda. And I did not give these additional nice properties that mu lambda satisfies, so let me give it now. So further, mu lambda satisfies the following properties. So the first property is that for U open in X, mu lambda of U is the supremum of lambda f such that f is less than U, and the second property is that for K compact in X, we have that mu lambda of K is the infimum of lambda f such that K is less than f. So remember that this is again the notation that we used before. So this means that 0 less than f less than or equal to 1, and the support of f is inside U. This is what f less than U means, and K less than f means that again 0 less than or equal to f less than 1, support of f is compact and f is identically equal to 1 on K. So in addition to being a Radon measure, this mu lambda satisfies these two properties where its values on open sets is given by the supremum of these lambda f's, where f ranges over functions which are which have compact support inside U, and which are taking values only between 0 and 1, and similarly for K compact the value mu lambda K is given by the infimums of these values lambda f, where f ranges over all functions which have compact support and range between 0 and 1, and which are identically equal to 1 on K. So let us look at the proof of the Riesz representation theorem. Now there are many proofs available, and I have decided to follow the proof in Folland's book. So for the proof I will follow Folland's book, which I found, the proof I found to be quite nice, so I will follow that. So this is theorem 7.2 in Folland's book. Now we begin by taking property 1 above as a definition. So this means that if U is open, then we define mu U to be the supremum of lambda f such that f is less than u. So we take this as a definition for the measure mu u for u open, and now we define mu star of E. So now E is an arbitrary subset of X, and then we can define mu star of E as the infimum of mu u, such that E is contained in U, which is open. And we claim several things, so this proof will require several steps which shall prove various properties of mu and mu star. So let's list them one by one and try to prove them. So we make the following claims. First one is that mu star is an outer measure. So the mu star that we just defined is an outer measure. So if mu star is an outer measure by Carathéodory measurable extension theorem, we get C mu star x, which is the sigma algebra of all Carathéodory measurable sets. Carathéodory measurable sets in X with respect to the outer measure mu star. Now the restriction of mu star, so we denote the restriction of mu star to C mu star x. This is a measure and this is denoted by mu. So this is again due to the Carathéodory extension theorem. Now we set our B lambda to be precisely this sigma algebra of Carathéodory measurable sets. Now the second one is that all open sets are in B lambda, and this implies that the Borel sigma algebra sits inside B lambda, because the Borel sigma algebra is the smallest sigma algebra containing all open sets, and B lambda contains all open sets. So the second claim is that all open sets are Carathéodory measurable. Thirdly, we have, so because all Borel sets are inside B lambda, we have that all compact sets are also measurable, Carathéodory measurable, and we have that mu satisfies property 2, which is that mu k. So if k is compact, this implies that mu k is the infimum of lambda f, such that k is less than lambda. So this was part of the additional property of mu on compact sets, and what we are claiming here is that once we define property 1, once we take property 1 as a definition, then property 2 follows for compact sets. And lastly, that the relation lambda f equals f d mu holds for all f in CCX. So let's prove these claims one by one. So proof of the first part. So we have to show that mu star is an outer measure. So if we show that for any arbitrary subset E, we have that mu star E is the infimum of these sums mu u j equal to 1 to infinity, such that E is covered by the union of uj's j equal to 1 to infinity, and all uj's are open. So if we show this, then this implies that mu star is an outer measure due to the lemma that we once stated, which was for due to the following lemma. Let me write it down. Due to the lemma, so this lemma said that if E is a collection of subsets of X such that phi, so the empty set and the entire set X both belong to E, and a rho is a map from E to 0 infinity, then mu star of E, so for E in X, mu star E given by the infimum of a rho E j equal to 1 to infinity, such that E is a subset of the union of ej's j equal to 1 to infinity, and ej belongs to this collection E. This is an outer measure. This is an outer measure, and this was proved. I think I left it as an exercise, but I said that the proof is exactly as you would prove that the Lebesgue outer measure is an outer measure. So I left this proof as an exercise. So here our rho is in fact this mu. This is our rho, and our E is the collection of all open sets in E, open sets in X. So then if we show that this equality holds, then mu star will be automatically an outer measure. So to show this, note that it suffices to show that if u is open uj infinity, such that uj is open for all j, so u itself is open, u is open, then mu u is less than or equal to this sum j equal to 1 to infinity mu uj. So this will imply that the infimum over these sums j equal to 1 to infinity mu uj, says that E is covered by uj's, uj open, and this is equal to the infimum of mu u, such that E is covered by a single open set U. So we just have to show that if U is open and given by a countable union of open sets, then it satisfies the this is the countable subadditivity property. Subadditivity property. So So note that by definition, we have that mu u is the supremum of lambda f such that f is in U. So in turn it suffices to show that for any f less than u, we have lambda f is less than or equal to this sum mu u j equal to 1 to infinity. So then we can take the supremum on the left and we will get mu u. So how do we show this? So let us fix a function which has compact support in U and whose range is between 0 and 1, and let k be the support of f, and this sits inside U. Now U is this union of UJs, and so this is an open cover of the compact set K, and this implies that there exists a finite collection say U1, U2 up to Un such that K is contained in the union, in the finite union of these n open sets U1 to Un. And now I am going to use the existence of partition of unity phi I. So there exists a partition of unity phi I subordinate to the cover Uj, j equal to 1 to n. So j equal to 1 to n here also, such that summation phi j is identically equal to 1 on k. So this is j equal to 1 to n. So now this implies that lambda f can be written as lambda f times j equal to 1 to n phi j, because k was nothing but the support of f, and so on the support of f this sum is 1. So f is equal to f times sum of phi j, j equal to 1 to n, and by linearity this is j equal to 1 to n lambda f times phi j. Now each f phi j is supported inside uj is less than uj. So this implies that lambda f phi j is less than or equal to mu of uj, and so this implies that lambda f is, which is equal to j equal to 1 to n lambda of f phi j is less than or equal to the sum j equal to 1 to n mu uj, and this is less than or equal to j equal to 1 to n 1 to infinity mu uj. So this proves that this mu star is an outer measure. Now for the second claim, we have to show that if U is open, U belongs to the sigma algebra of Carathéodory measurable subsets, which is equivalently saying that mu star E equals mu star E intersection U plus mu star E minus U for any subset E in X. So it suffices first, so if we reduce the problem twice. So first it suffices to show that mu star E is greater than or equal to mu star E intersection U plus mu star E minus Q, because the other inequality is obvious due to mu star being an outer measure. So by countable subadditivity, mu star E is less than or equal to the right hand side. So we have to show that mu star is greater than or equal to the right hand side. On the other hand, if mu star E is infinite, there is nothing to show. So we can only we can restrict our case, our attention to the case if mu star E is finite, then this holds. We can also make a second reduction, which is that by outer regularity, it suffices to show this, to show the inequality if E is open, and still we have mu star E equals mu E if E is open. This is finite. So now we have to show when E is finite, when E is open of finite measure, we have to show this inequality. Now if E is open, if E is open, this implies that E intersection U is open, and this means by our very definition of mu star, so mu star E intersection U is now mu of E intersection U because it is open, and now this is equal to the supremum of lambda f such that f is less than E intersection U. So now given epsilon greater than 0, choose f less than E intersection U such that lambda f plus epsilon, or rather lambda f is greater than or equal to mu E intersection U minus epsilon by 2. Similarly, now that we have chosen a function f of compact support with support inside intersection U, we have E minus support f is open. So choose G in less than E minus support f. Note that support f is compact, so it is closed. So the complement is open. So this is why E minus support of f is open. So now we can again choose G less than E minus support f such that lambda G is greater than or equal to mu of E minus support f minus epsilon by 2. But the way we have chosen f and g, this implies that f plus g is less than E, because when g is 0, when f is non-zero, g is 0 and vice versa. So f plus g is still between 0 and 1, and its support is now contained in E. So this implies that mu E is greater than or equal to lambda times lambda of f plus g, which is equal to lambda f plus lambda g by linearity. And now we have chosen f and g, so that this is greater than or equal to mu E intersection U plus mu E minus support f minus epsilon by 2 and epsilon by 2 make an epsilon. But since support of f is contained in in u, so this implies that this is greater than or equal to mu E intersection u plus mu E minus u minus epsilon. So this is because support of f is contained inside E intersection u, which is inside u. So mu of E minus u is less than or equal to mu of E minus support of f. So this shows that all open sets are indeed in the sigma algebra of Carathéodory measurable sets B lambda. So this proves our second claim. Now the third claim is that mu satisfies property 2, namely that if K is compact, then mu K, note that K is Carathéodory measurable because it is a Borel set, and Borel sets lie in the sigma algebra of Carathéodory measurable sets. So now we have to show that this is the infimum of lambda f such that K is less than f. Now recall that by definition we have that mu K is equal to the infimum of mu u such that K is contained in u and u is open. So let me denote this right hand side here by lambda 1 and the right hand side here by lambda 2, and I am going to prove that lambda 1 is equal to lambda 2. So first note that if u is open such that K is contained in u, then by Urysohn's lemma, there exists a function f which is continuous with compact support such that K is less than f is less than u, and so this implies that lambda f is less than or equal to mu u, because this latter on the right hand side was the supremum. By definition this is the supremum of all such. So let me write here h such that h is less than u. So this means that lambda 2 is less than or equal to lambda 1. So now we will prove the reverse inequality. So let f in CCX such that K is less than f. Now we have to find an open set such that f is less than u epsilon. So how do we do this? So I let epsilon greater than 0 and take u epsilon to be the set of all points in X such that fx is greater than 1 minus epsilon. So because f is continuous, this set is open. Now we immediately have that since f equals 1 on K, K is a subset of u epsilon, and also if G is less than u epsilon, then we have that lambda g is less than or equal to 1 minus epsilon inverse times lambda f, since because fx is greater than 1 minus epsilon, so this means that 1 minus epsilon inverse f minus g is greater than or equal to 0, because this is strictly greater than 1 and this is between 0 and 1. So we have this inequality which shows that lambda g is less than or equal to 1 minus epsilon inverse times lambda f. And now if we take the supremum on the left hand side, this means that mu of u epsilon is less than or equal to 1 minus epsilon inverse lambda f, and so letting epsilon goes to 0, this means on the right hand side, on the right, well, first of all, this means that mu k is less than or equal to mu u epsilon, which is less than or equal to 1 minus epsilon inverse lambda f. And now we can take epsilon going to 0 on the right hand side, so this implies that lambda k, mu k is less than or equal to lambda f. So this shows that lambda 1 is less than or equal to lambda 2, and so these two quantities are in fact equal. So this equality holds. So we have also proved the third assertion. Now we will derive some consequences of this third assertion.